Okay, geometry, you're on a roll here. 9-7. We're finishing the chapter. I'm proud of how you are able to take this on video lessons. So pause, give it a try. Okay, hopefully you remember that when you have a vector notation like this, you're just going to increase the x values all by 2 and the y's all by 2 in this case, right? And so we end up with 4, 1, 6, 5, and negative 3, 6. Good. What would the value of JK be? AB is 4, and it's similar to JK, right? So you've got a little proportion, probably 3 to 4 is as 4 is to 5 1/3. So today we're going to draw some dilations, which you have done before. We're going to talk about center of dilation, enlargement, and reduction. Recall that a dilation is a transformation that changes the size of a figure, but not the shape. So let me grab a figure, grab this one. So here's a figure. A dilation won't change the shape, but it's kind of like what I'm doing when I do this, right? Good. Okay. The image and the pre-image of a figure under dilation are similar. So if I clone that, if this here is the pre-image and this is the image, look at, they're similar. So tell whether we have a dilation or not. Does this blue to red appear to be a dilation? Not. We have long blue sides and then we have shorter, right? But the little ends appear to be kind of, I don't know if they're even really similar, huh? How about in part B, what would you say? Sure, they look similar. The figures are similar and the image is not turned or flipped. So simply a dilation. So for a dilation with a factor k, remember it's multiplication, isn't it? If k is greater than 0, the figure is not turned or flipped. But if k is less than 0, if you're multiplying by a negative, then the figure will be rotated by 180 degrees. So our rules for dilations: a dilation or similarity transformation is a transformation in which the lines connecting every point P with its image all intersect at C. That would be the center of dilation. So C to P prime over CP is the same for every point. That ratio of C to the image over C to the pre-image is going to be the same ratio for every point. So CQ prime over CQ would be the same as CP prime over CP. The scale factor, K, of a dilation is the ratio of a linear measurement of the image to a corresponding measurement of the pre-image. In the figure here, K is PQ to PQ, PQ prime to PQ. So a dilation enlarges or reduces all dimensions of proportionally. A dilation with a scale factor greater than 1, so if you're multiplying by a factor greater than 1, what would you call it? Yep, enlargement. If you have a scale factor that is less than 1 but greater than 0, so we're not negative, we're just a fraction, it would be a, reduction or a contraction. Okay, I wanted you to walk through a dilation before trying one, so here we have the example shown. You're asked to copy the figure, and the figure is given here, WX, they call it WXYZ, WX, it looks like ZY, the way they've drawn it here. Remember, you need to name vertices in sequential order, consecutive order. Anyway, under a dilation with a scale factor of 2. So basically, what you do is to draw a line through P because they're giving you this center of dilation at P. So you draw a line from P through each vertex and just extend it out. Just jet those lines out, kind of like we did with vectors. And then you need to measure the distance from P to each vertex, and then you need to mark the distance twice as far from P to the image of X. So if it is a length of 1 from P to X, then you would go a length of 2, or 1 times 2 to get from P to X prime. Let's say it's a distance of 1.2 to get to W, then we would go to 2.4. We would multiply 1.2 by 2, and we would get to 2.4 to get to W prime. The second example, we are asked to dilate RSTU by a scale factor of 3. So once again, through center Q. There's a Q point out here, and you can see that a ray has been drawn from Q through each vertex of this quadrilateral. Q goes through R and beyond. Q goes through S and beyond. Q goes through, there's a T back here, T and beyond, and through U and beyond. And then, because we're asked to dilate by a scale factor of 3, notice their terms here. On each line, mark twice the distance from Q to the vertex. So if we go from Q to R, if this equals 1, then we have to go twice that from R to R prime, or we go 2, right? So we are increasing the distance from Q to a total of 3 units, 3 units from Q. If Q to R is 1 unit, then Q to R prime is 3 units. Okay? Let's imagine that from Q to S is 2 units. And so we would travel from S to S prime twice that distance, so 4 units, right? Or going from Q to S prime would be a total of 6 units. Okay? And so on. So we have increased by a scale factor of 3. So, if we have a sketch of a flower that is 4 inches, is represented by 1 inch on the actual flower, then if the flower has a 3-inch diameter in the sketch, what would the diameter be in the actual flower? Okay, so see if you can pause and try this and come back. Okay, I always like to think of these problems as model over actual. And so in this case, if we have 4 inches over the actual 1-inch flower, so it's 4 over 1, then if the flower has 3 inches diameter in the sketch, then we could set this up like this. Model, oops, not connected, just a second. Model over actual equals model over actual. I love using proportions for this kind of thing. So 4 inches is the model over actual 1 inch. And if the flower has 3 inches diameter on the sketch is in the numerator, 3 inches, equals what diameter of the actual flower, right? So we can cross multiply, right? We can cancel our inches here. Bring the x up, and we end up with 4 x's equals 3 inches. And so when we divide by 4, we get x equals 3/4 of an inch. Okay, so the diameter of the actual flower would be 3/4 of an inch. Okay, check this out. What if an artist is creating a large painting from a photograph into square and dilating each square by a factor of 4? Suppose the photograph is a square with sides of length 10 inches. What would the area of the painting be? It's kind of phrased strangely, isn't it? An artist is creating a large painting from a photograph into a square and dilating each side of the square by a factor of 4. Okay, so it would be the sides, right? So suppose in the photograph the square has side lengths of 10. What would the area of the painting be? if it's a square, then we know that the area of the photograph would be 10 on each side, right? 10 times 10, or 100 inches squared. So if we're going to dilate it by a factor of 4, then we would multiply each side of the square. Imagine a square, which was 10, right? By 10, we're going to multiply each side by 4, right? By 4. So we'll end up with 10 times 4 inches times 10 times 4 inches, which is 40 inches times 40 inches, which I'm sure you know is 1,600 inches squared. So we went from a 100 square inch photograph to a 1,600 square inch photograph by dilating each side. That's when you square the side, an area, you end up having a dramatic effect on the area, don't you? When you square those dimensions. If we take dilations to the coordinate plane, we can see that if point P is at xy, and it is the pre-image, it would be the pre-image of a point under dilation centered at the center, the origin, with a scale factor of k. We would have the image point at kx, ky, right? So in order to dilate a point whose center is at the point of origin, we simply multiply each of the coordinates by the factor k. If the scale factor is negative in a dilation, you know that it ends up rotating by 180 degrees. So imagine if this point is at 2, 2, and we were multiplying by, let's say, a factor of -1, we would have -2, -2, and it would end up in this quadrant 180 degrees from where it was. So if k is greater than 0, the dilation with a scale factor of -k would be the composite of dilating by k and then rotating 180 degrees about the center of dilation, right? So it'd be like, blow it up by something bigger than 1 and then rotate it 180 degrees. Okay, so draw the image of the triangle with these vertices under a dilation of a scale factor of -1/2, centered at the origin. So because it's a scale factor of -1/2 centered at the origin, we simply multiply each term in the ordered pair by -1/2. We're going to see that 180 degree rotation, aren't we? And are we going to see a enlargement here or a reduction? Good, we're going to see an enlargement, right? So when we multiply here -1/2 times the -4 and so on, go ahead, pause and get these numbers, and you should have 2, -2, 1, 1, and -2, 0. Good. So you can see that this triangle was interesting because it crossed the x and y axes, didn't it? So P shrunk by the half and then rotated, right? Q shrunk by a half and then rotated, right, to this position here. R shrunk by a half and rotated. And so we have this really interesting new image. Okay, you try this now with the given coordinates. And on the next slide, I provided you with a place to put it. So go ahead and try it by pausing the video and come back and check out what you see. Okay, I hope you paused it if you needed to. And if you're back, you should have changed your coordinates to these given coordinates, right? It doesn't change R at all, does it? But it does change S and T, okay? And so we ended up with something that looks like this. Okay, so we had the original, and notice R stays in the same position, but we have this 180 degree rotation and reduction in the image. Quick quiz, does this appear to be a dilation? Yes. Can you dilate this by a 1/3? Go ahead and pause and draw it out. And it should look something like that. Try number 3 and then we'll skip number 4. Come back and check your work. And you should have 240. Good job. We've already done enough of 4, so here you go. Have a good time.